Hello everyone. Hello everyone. You are welcome to this channel. Today we shall be discussing numerical solutions of partial differential equations. All along we have been discussing ordinary differential equation, but in partial differential equations we have variable u and is varying with more than one independent variables like x and y in this case. So as a result of that, it becomes partial differential equation because u is varying with more than one variable. So example is shown here where the temperature is varying with time and it's also varying with x direction. To solve the partial differential equation, we have the numerical solutions known as finite difference. We have another one called finite volume, and we have another one called orthogonal collocation. So in this tutorial, we shall be looking at finite difference method. To do the finite difference method, we need a discretization of our grid. And to understand this, we already know our Cartesian plate to be what? Y and X. So this is what we use to discretize our space. So that is what we refer to as grid. So the space in the body we are examining, that is what we put into the Cartesian plane to discretize. So how do we do that? For example, now, if this is the body where the temperature is varying or the water is flowing or whatever we are examining, so we discretize it into different divisions like this. And we look at the variable at this node, at another node, at another node, at another node. So if we are looking from it from this point, let's say this is our point, the center point, 0, 0. So that means our x is 0 here and y is also 0. By the time we get here, we are moving along the x direction. We are moving along this x direction. So that means our x has increased by 1. So from initial point 0, or let's say I here and j here. So then it has increased to I plus 1 here and j remains the same. So if we come back as well, it has reduced by I minus 1, but j remains the same. Similarly, if we look at it vertically in the y direction, that means our j is increasing here, but I remain the same. I remain the same, but j has increased plus 1. Similarly, if you come down here to this point, it means our height still remains the same on the x, but j has reduced by 1. So and so on. That is what they refer to as discretization. So a good example is illustrated here. So we can see this is the center point ij. So I refers to the value in the x direction and j refers to the value in the y direction. So this is the center point ij. If you move to the right on the same line, if you move to the right here, it means our height has increased by 1, but j remains the same. If you move back here, it means our height has decreased by 1 and j remains the same. If we move up here, it means our I remains the same, but j has increased by 1 in the y direction. If we come down as well, our I remains the same, but j minus 1, j has reduced by 1. Similarly here. So just we are moving in the Cartesian plane. So once we have understood that, then we employ the Taylor series. So the Taylor series states that to determine the value of a variable that is varying with more than one independent variable like this, at the next point, it means you get the value at the last point plus h. H is the step size, just like we learned in the numerical method. H is step size, and then the differential with that in the line of x. So plus, if we are going to the second differential, then 1 over 2 prime a squared, the square u dx square. You know we are moving in the x direction and so on. Similarly, If you want to step back, this is when we are stepping forward. But we want to step back, we want to move backward. That means ux minus h, we are looking at the value of u backwardly. So it was uxy minus h minus this, plus this minus this. So in that case, we see the equation 1 when we are adding step forward, and the equation 2 when we are moving backward. So to simplify this, let's subtract 2 from 1. Subtract 2 from 1. If you do that, it means u and u will cancel. This one will cancel this. This we add to this. This we also cancel this. So if we neglect the higher power here, if we neglect all the higher power, therefore, we are going to be left with du dx expression, which shows that the partial differential of u with x is equal to 1, is approximately equals to 1 over 2h this ux in the front minus u backward to get the value of du dx at the point xy. Similarly, if you do that for the same y direction as well, up and down, we are going to arrive at a similar thing, but in this case will be ux y plus k minus ux y minus k. Similarly, if you look at the equation as well, we can also get expression for d square u dx square. How do we do it? It means if we had equation 1 and 2 together, that means if you had equation 1 and 2 together, something interesting will come up here. Something interesting will come up here. It means this and this will be added, u plus u, that will be 2uxy. Then this and this will cancel out. This and this will cancel out because once you add them, they will cancel each other. Then this and this will also be added. That will be 2 times that expression. And let's assume we neglect everything afterward. So in that case, we are going to arrive at something like this. The square u dx square is equal to 1 over a square, this, and that. So these are the values we shall be using to resolve our partial differential equations problem. So let's look at an example. Example is given here that the four sides of a square plate of side 12 cm made of homogeneous materials are kept at constant temperature as shown below. So this is the material. This is the material, and it has side of 12 cm each. Everywhere is 12, 12, 12, and 12. And they keep the side at constant temperature. Below here is 100, 100 here, 100 here, and the top here is 0. So the flow of the heat in the material follows the heat equation. So they gave us the physical law and the mathematical expression guiding the flow of heat in this material. Use grid size of 4 cm. Find the steady state temperature. Find the steady state temperature at the mesh point. So simply put, we are to discretize our system. We are first of all to discretize our system. So let's discretize like this. So it's 12 cm here, 12 cm here, 12 cm. So there, and we are asked to use grid size of 4 cm. That means we are going to divide into 3. So we are going to divide into 3. So this will be 0, 4, 8, 12. This will be also be 0, 4, 8, 12. So remember, we are working in the Cartesian plate. So this is the y direction and this is the x direction. So you remember again that this side is kept at 100 degrees Celsius, this side at 100 degrees Celsius, this side at 100 degrees, let me write 100 degrees Celsius, and this side is at 0. So now what we are asked to do is to look for find the steady state temperature at the mesh point. At the mesh point. So at the steady state, remember one thing. Yeah, dt equals to the square x, the square t, sorry. So at steady state, this expression will not change with time. It means it doesn't change with time, and it becomes 0. So we are having the square t dx square plus the square t dy square equals to 0. So this is the expression we are going to apply to this grid. So I remember we are told that what? Find the steady state temperature at the mesh point. What are the mesh points? Mesh point are the internal side of the grid. So 1, 2, 3, 4. And again, you are going to notice something. This is the center point that we have chosen. You can choose your own convenient center point. So that means t at point x0, y0. So if you move along this side, this will be t at point 1 in x and 0 in y. This will be t at point 2 in x and 0 in y. So if you move up, this will be t 0, but y has increased to 1. And this will be t 1 of x, and y is also at 1. And t at 1 of, 2 of x, and y remains at 1. If we move up here, that means our x remains the same, which is still 0, but our y has increased to 2 here. So, and when we got here, to what? T remains 1, but the y is still at 2, and here the x has goes to 2, and our y remains at 2. So those are the points. So we are looking for the internal point. We are looking for T11, T12, T21, and T22. So those are the 4 points we are looking for, because those are the mesh points, the internal point. So how do we go about it? So we are going to apply this expression to them. So this is it, and we are going to find those 4 points now. So how do we find those 4 points? So to find T11, let's look at an example. To find T11, we are going to invite our expression, which is what? The square u dx square xy is equal to this. So how do we use this expression now? Our h is 4. You remember that our h is 4, which is our step size. So that means it will be 1 over 4 square, because we are looking at it at xy. Xy is at the point we are targeting now, which is T11. So we open the bracket, and u is what? U is x plus h. We move forward by 1. So when we move forward by 1, what do we get? At the point T11, we are standing here. This is our center point. We want to move forward. That will be, we are getting to T21. T21. So that means we are going to say here is T21 minus 2. What is uxy? That is where we are standing now, which is our what? T11 plus minus the x minus h. Let's look at what is at x minus h. This is at T01 here, and remember, everything at this boundary is at 100. So that means this will be plus 100 at that point. And our expression is what? We have to add the x side to the y side. So we'll go back here. We said plus, this is our x side, the square u dx square. So we have to add it to the y side. So at the y side, our grid size 1 over k square is also the same grid size, which is what? 1 over 4 square. So, and then we say ux yk. We move up now. We are moving up. Y plus k. X remain the same at the point. So this is our standing point, which is at T11. It's at T11. So we move up. When we move up at y plus k, that will be our T12. So we had that there. So we had that will be T12 minus, what is the next value there? Minus 2uxy, which is still our standing point, 2T11 plus uxy minus k. We come down now. When we come down, what do we get? What do we get? When we come down from T11 down here, that will be at the boundary, which is 100, which is kept at 100 here. So we had plus 100 here. So when we solve that, we are going to, so everything when we had them, we have said as steady state, the addition of the two of them, the square t dx square plus the square t dy square will give us 0. So what do we get there? It means 1 over 16 into T21 minus 4T11 plus T12 plus 200, everything equals to 0. So by the time you do that, we can arrange. So we can arrange it so that 16 will go there and cancel out with 0. Then we are going to have expression like this. So by the time we do that for when we did what we did now for the T11 point is this. Now we go next to, let's say, T12. And we do for T12, we are going to get its own 2. Then we go next to T21. When we do that, we are going to get its own expression 2. When we do that for T22, we are going to get its own expression. Then we are going to arrive at a matrix format like this. So when we do that matrix, we remember our matrix solution. We can use Cramer's rule or matrix method. And we resolve it to that. We select all the coefficients. We have all the variables. And we have all the right side of the equation. So we can use the matrix method, and it's going to give us these values at each of those positions that we have assembled. And that is that to employ finite difference method to solve our partial differential equation. I hope you have enjoyed the tutorial. If you have any comment, please send me anyone below, and don't forget to hit the subscribe button. Thank you.